All right. Thank you so much for having me here today. Today I'm going to be sharing with you various application examples that use Chapel's task parallelism concepts. So there's a very big team behind Chapel these days. I am the lead, as Ram mentioned. The tech lead is Brad Chamberlain, and we have a number of developers. Some of them are sub-team leads. We've got various sub-projects going on. We also have a visiting scholar from NCAR with us this year, Scott Bachman, and I'll be sharing some of the codes that he's been developing recently as well today. So for those of you who are not familiar with Chapel, Chapel is a general purpose programming language, and it's been developed specifically to ease parallel programming for high performance and for portability. So we'll really work towards people being able to develop their codes on a laptop and then moving it to a supercomputer. And Chapel started back in 2002 with the HPCS program that DARPA was running, so high productivity computing systems. And it's been funded up until this point, continuously since then. It's gone anywhere from 5 developers to now we're up to a team of 21. So one of the big milestones for the Chapel programming language was the development of the Arcuda data analytics framework. So this is an open source framework that I'll be talking about some today, and it's used in production and has been used in production since 2019. And that has helped with the support of Chapel. And then there are various other applications I'll be talking about today being used in research that are written in Chapel as well. So let's talk about some of these applications. They're using Chapel by being like rewritten from other languages into Chapel. Champs is an example of that in the upper left-hand corner. Champs is a 3D computational fluid dynamics code looking at simulating the airflow over airplane wings. It's being developed by Eric Larendow's group at Polytechnic Montreal. And that is the largest application that we're aware of that's been written in Chapel. It's about 100,000 lines of code. Arcuda is the one in the lower left. The Arcuda model is you actually have a Python front end, which is the client, and then there is the server, which runs on the supercomputer and accesses massive amounts of data, is written in Chapel. And so that is open source and has been developed by my Carolina developers at Department of Defense. A couple of other examples, more on the research side, are Chapel Ultra, which is simulating ultralight dark matter. That's been one that's been developed for many years at Yale. And in that application, it's using distributed computation in Chapel, and in the main performance bottleneck in that code is a distributed FFT that's being done. One of the applications I'll be talking a little bit about today is called CHOP, and this is a Chapel-based optimization code doing some branch and bound optimizations, lots of irregularity in this code. And it's also doing something interesting. It's calling out to CUDA. It's using Chapel for the distributed memory parallelism and to write the load balancing, but then it's calling out to CUDA to help do the solve. So why are these applications using Chapel? Well, it's fast, right? So it's easy to use and it is fast. Some examples of how fast it is, in the Arcuda data analytics framework, we've got a sort that we've got some runs, and I'll show you the graph later, where it's within 2 to 3x of the world record in terms of sorting. The visiting scholar I mentioned, Scott Bachman, he's been doing some comparisons of DASC usage in his community. So his community is climate scientists, and they've been analyzing a lot of data, and he's looking at ways to potentially leverage Arcuda in that. He did a comparison of like loading HDF5 files, doing gathers, scatters, and streams, And in all of those, the Arcuda implementations of those were significantly faster than Dask. And then Arcuda can do things like group by and argsort, which Dask doesn't have available now. In the CHAMPS code that I mentioned, it has performance and scalability that's competitive with MPI and C++ codes that are doing similar kinds of simulations. And one run that we're aware of is a run where CHAMPS scaled up to 256 nodes on a Cray XC. And in that experiment, there were 640 million cells in the 3D grid. I think there was a mention of 100,000 grid points. This is 640 million grid points. And then in the coral reef code, and this is a code that Scott has been developing essentially in the last 2 months. It's already up and running. He took a computation that was originally written in MATLAB. He's rewritten it in Chapel, made some algorithmic improvements as well, and now that algorithm that used to take days is taking seconds. And his collaborators and other collaborators doing coral reef analysis are paying a lot of attention to this and starting to ask him to do more and more, and giving him bigger data sets. So that's very exciting. So this workshop is about mini-task, asynchronous mini-task computation. So let's talk about what Chapel tasks, what it means to be a task in Chapel. So in Chapel, a task is a unit of computation, and it's typically run in parallel with other tasks. Tasks can share data, and because Chapel has the concept of this global namespace, the way tasks share data is through the lexical scoping of the variables that they're using. Tasks, of course, can also have data that's only local to themselves. The way tasks are mapped to various nodes in a machine is either explicitly by the programmer using a concept called locales. Say, I want this task to run on this locale, or implicitly using some of the higher level parallelism constructs such as for all. Now, underneath it, for all is also being explicitly mapped. And what's especially nice about that is that you can have user-defined iterators that change how the for all is mapping tasks to nodes. And a couple of the applications I looked at here do that. So in Chapel, tasks are going to execute indefinitely until they yield control explicitly or through synchronization constructs. All right, so at this point, are there any questions about tasks in Chapel? It's hard to see you all. Got a very bright light in my face. Yeah, questions?
Yeah, one question about that. So can different tasks be mapped on different GPUs, for example?
Yeah, and I actually have a slide towards the very end of the talk giving just a flavor of the kinds of work we're doing for GPU support. Yeah. Mm-hmm. Yes, right.
So that tasks share data through the lexical scoping. Is there anything to help programmers avoid race conditions on shared data between tasks?
That is an excellent question. So, so the question, I'm just going to repeat it for the stream, is that is there anything to help programmers avoid race conditions? And there's some. So there's atomic and sync variables, but you do have to manage that. If you're coordinating between tasks, you need to either know you're in a fully parallel loop, or you have to be doing the coordination between the tasks in a way that you don't end up in live log. So, all right. In other words, the programmer can hang themselves. Yeah, unfortunately. All right, Damien, did you have a question?
So you mentioned synchronization. I'm wondering if there's also looser forms of coordination and semaphores.
There is looser forms of computation, and thank you, because this is the next one. All right, okay. All right, so so there, this is the overall set of constructs that Chapel has to support task parallelism. We've got the synchronous parallelism at the top here, and then asynchronous parallelism, which is going to help answer Damien's question, and then some higher level parallelism abstractions. So for synchronous parallelism, we've got the co-for-all, and I've got a picture in this upper right here of what that kind of looks like. The task that is doing the co-for-all is going to start a task per iteration of the loop, and then it is going to wait until all of those tasks complete before it finishes up. And in the applications that I've looked at, there's co-for-all is being used a lot. It's used with the on clause to map different tasks to distributed locales across nodes, and then it can also be used nested in that to have parallelism over multiple cores on the machine. There's also a covariant construct that instead of spawning off a task per iteration, it's just spawning off per statement that's in that covariant block. For asynchronous parallelism, we have the begin, it's kind of like a spawn, similar to spawn, and that creates an asynchronous task. You can see a picture of this. I've got one task on the left that is actually doing 2 begins, and when you do a begin, that spawns off a task, and that task itself can then spawn off a task. And in fact, this idea of nested parallelism works in any different combination in Chapel. So you can have synchronous with asynchronous, and you can really shoot yourself in the foot with, if you're not careful in terms of how you're coordinating between tasks. And then the way that you coordinate between tasks is the sync and atomic variables. I'm also going to show an example where you can spawn sub-processes, because there's one of the applications I looked at right in Chapel is actually taking advantage of that. Spawning sub-processes is essentially like doing an exec. And then for higher level parallelism, we have the for all. Then there's the for each. For more lower level, like vector parallelism or parallelism on the GPU. And then we have operations like scan and reduce that are also distributed and shared memory parallel. Okay, any questions on this? All right. Okay, so today I'm going to be talking about some of the observations I've made of these various applications. So I've been in the Chapel group for a couple of years. You know, before that, most of my work was sparse tensor computations and very focused on that. I kind of kept an eye on what Chapel was doing and was interested. And so I've really been educating myself over the last couple of years of like, well, how is Chapel being used in applications? And so this is a little bit of a deep dive into what are some of the things that we're seeing. And you can kind of see from a glance with all these applications, there's a lot of co-for-all being used. It's a lot of synchronous parallelism, actually. In fact, at the beginning of this week, I was like, where's the use of begin? And so I went ahead and made a little toy example that computes an arbitrary task graph so that we'd be able to look at at least one example of that. So there's not a lot of asynchronous parallelism that people who are writing large applications in Chapel are actually using. They're taking advantage of the synchronous parallelism. Okay, so this is the magic table for this talk, as it were, where I've got all of the different applications I'm going to be talking about, benchmarks and applications, and then the kinds of task parallelism in Chapel that they're using. You can't see at the bottom, but maybe this is for the best. There is a poll everywhere link, but I unfortunately can't get on the internet in this room for some reason. So the poll everywhere isn't going to work. So I'm so sorry. You won't be able to do that interaction. But it won't bother you because you can't see this at the bottom. All right. So I have to actually be on the internet to turn on the poll everywhere. So for people who are remote, you can go to the link, but it's just going to have the survey for the end of the talk up, which feel free to fill out. All right, so the first question was, and see now it's like, where's the internet? Okay. All right, come on. See if we can get past that. Okay, great. So let's start out with our hello world. So with the, let's first talk about this idea of a locale in Chapel and what the execution model is in Chapel. So a locale is a concept, it's a first-class concept in Chapel where it's something that you can run tasks on and you can store variables on. We're mostly talking about the run tasks piece today. So think compute node on a parallel system. So in the diagram I have here, I have 4 compute nodes, those rounded rectangles that are turquoise, those are my compute nodes, and then I have a locale on each compute node. How is this implemented? Each locale is a process. Typically, there's a one-to-one mapping between locales and compute nodes, although we do have some new features that just came out, or I think are coming out in our release next month, where you can have like a locale per socket. But for today's talk, let's just have the 4 nodes that exist in all slide presentations and the 4 locales that are going to make map to them. So when you start your Chapel program, you essentially tell the runtime systems, here how many locales I want you to launch my program onto. And then in the program itself, the program can refer to these locales through the locales array. All right. So when that main starts in your user code, there's going to be one task on locale 0 that starts up. All right. And then I'm going to be showing you how some of the constructs in the language enable you to start up other tasks and then map them to other nodes. So let's start out with that first conceptual, we're just on one node, and think about how shared memory parallelism happens. So we have this keyword here, which refers to the current locale we're on. So right now, that's just going to be locale 0. And then you can actually ask some information about these locales, like how many processing units is on this locale? Or what is that locale's name? And then in a co-for-all loop, which is going to create a task per iteration, we can essentially say, all right, I want to create a task per processing unit that is on this machine. Okay? You're not getting into control like how those tasks are mapped to those threads. That's done underneath the covers, but you do get to control how many tasks you create. So if I were to run this, then I get the little hello world per thread happening. All right. So at this point, we've just had a shared memory parallel machine. We haven't referred to remote locales at all. So now let's add an outer loop that is going to iterate over that locales array. So this outer co-for-all, again, same semantics. It creates a task per iteration of the loop. But now what it's doing is it's using this on loc block, which is essentially saying, I want this task to be executed on this particular locale. Okay, so that's how we're mapping tasks to locales. And then inside of that, we can have that nested parallelism where more tasks are being created. So now we've got, a dot, because now we're going to have 16 hellos coming about. Okay, and now here's the poll everywhere, which is very upset that it can't get to the internet. So I'll just click past that. All right, but any questions at this point about co-for-all or hello world? Right, great. Well, let's keep going. Now let's talk about HPO. So this is a hyperparameter optimization code. And what it does is it has a Python interface and then a Chapel backend. so that you can optimize the different parameters that are being sent into machine learning training software. So when you're doing training for machine learning, there's often a lot of tweaking that has to go, how many layers do you need, how big are things, various other parameters. And so this program was written to take advantage of distributed memory parallelism and shared memory parallelism with Chapel, and then call out to the different programs that are actually doing the training and hand them different parameters. And so this code does use the coveralls to get at distributed and shared memory parallelism. But what I'm showing on this slide is how this code is also spawning off these asynchronous subprocesses. And this is available in the subprocess module. This is a standard module provided with Chapel. And there is a spawn function, which will spawn off a function, a subprocess. And you can see there that we're just giving it a command line of, hey, I'm going to call this train executable that's doing some kind of training, hand it some parameters, and then I'm going to capture the standard out. And then you can do whatever computation you would like. That's the ... While that subprocess is doing its thing, and then at some point you can do a process.wait to make sure that that subprocess completes and then process the output that comes out of it. All right. So the next one is Arcuda. And I'm going through these at a pretty big clip because I enjoyed looking at all these applications, but I want to be able to get through most of them and show you the GPU stuff at the end. But please do feel free to raise your hand and interrupt with questions. I can kind of see your raising hands. All right. So now let's talk about Arcuda. So Arcuda uses, I'm going to show an example with the coveralls, but it actually uses for all a lot in Arcuda. And it does that because Arcuda is primarily based on this distributed array concept. So an array that's been distributed across multiple nodes in the supercomputer. So Arcuda was that production application I was telling you about. So this is used in production on a daily basis these days on a lot of big machines. And what it is you've got a Python interface. So the data scientists are using Python and Jupyter notebooks, and that's the client. And what that's doing is it's communicating with a server that's written in Chapel through ZMQ socket programming. That's how those two are communicating. And it was designed so that the data scientists could kick off a sort or kick off a gather or scatter or some kind of data analysis. And then it would come and it would run on terabyte scale arrays, and it would come back in seconds and minutes. And that was the goal for Arcuda, and it has been the reality for Arcuda, which is why it's being used so frequently in production. It's about 30,000 lines of Chapel code. It is open source. It wasn't developed by the Chapel team, although definitely Brad Chamberlain was talking with Mike Merrill and Bill Roos as they were developing this code, but it was developed by those two at the U.S. Department of Defense. So why did they use Chapel? They had multiple reasons for that. They wanted a high-level language. They wanted it to be able to have distributed arrays over large machines. They wanted to develop on their laptops and be able to just run it on a supercomputer. But they also wanted something so that when something broke, because we all are programmers and so we know that things break, that the Python developers could actually look at under the covers and see how the server was implemented, and it would be somewhat readable, more readable for Python users. I don't have any hard data on that one, as to whether that's been achieved or not. But. Okay, So let's talk about this hero run that one of our team members did. Elliot did this. So he took 72 terabytes of data, and he did the sort in about 2.5 seconds over 73,000 cores, almost 74,000 cores. And you can see it scaling up as we go out to 576 nodes. Each of these nodes have 128 cores. And the code that does this is 100 lines of Chapel code. Okay. So this is the outline of that code here. But first, when I'm talking about the parallel patterns in our CUDA, as I said before, it's mostly using for all. But in this super fast radix sort that Mike Merrill implemented, and then we helped since then improve performance on with things like aggregation, etc. I'm not showing here. This is the outline of the computation. You have an outer sequential loop, for loop over the digits, because you're doing the radix sort. Then you have a nested code for all, giving you the distributed and the shared memory parallelism that's doing all the histogramming, counting up like how many of each digit I have. There's then a scan operation that tells us kind of where we need to put the numbers based on how many has each kind of digit. Think something like a compressed sparse row, like sparse data structure, if that's means something to you. And then we have another nested code for all, where all of the tasks then put the numbers that they're responsible for into this global array. All right. Okay. So now let's talk about CHAMPS. CHAMPS is this 3D computational fluid dynamics code. We talked a little bit about how Eric's group developed this. The kinds of computation that we see in this code are actually much more SBMD-like. Okay, so the very similar to what you would see in a lot of distributed parallel stencil codes. So you have a task per node. Each of those tasks are going to have their own local array. It's going to have a halo. You're going to do the computation over your part of the grid, and then there's going to be a halo exchange. And they're then getting threaded parallelism from overall. So there wasn't much here in terms of asynchronous parallelism. This was all synchronous parallelism we're using for this code. What I especially wanted to share from this group, though, is a quote from Eric. So Eric gave the keynote at the Chapel Implementers and Users Workshop in 2021. And here's what he had to say about Chapel. He says, so CHAMPS, that's the new solver that has been made and all made by students. So Chapel promotes the programming efficiency. It was easy for them to learn. I see the end result. We ask students at the master's degree to do stuff that would take 2 years, and they do it in 3 months. And I'm not joking, this is from 2 years to 3 months. So if you want to take a summer internship and you say program a new turbulence model, well, they manage, and before it was impossible to do. So that's a significant impact that CHAMPS has had for him. He actually has a very charming story about when he was a postdoc, a grad student and a postdoc. He took his PI's Fortran code and rewrote the whole thing in C++. So he found it quite amusing when he turned around and his students and postdocs had rewritten the code and added more functionality in Chapel. So this is a code that is, it is being used for research, but it's also participating in international workshops to figure out how to predict things like icing and lift prediction of wings. And it is getting, it's competing with longer lived and more established codes at places like Stanford and MIT. All right, now let's talk about chop. So this one, I figured, okay, this is gonna use begin all over the place. It's a tree-based, branch-bound optimization algorithm. You've got an irregular tree, there's lots of pruning. I saw a figure like 95% of the tree is actually gonna get pruned, like somewhere over between 90 and 95% is typically pruned. And Tiago's the developer of this. He's got some examples of doing this for like an in-Queens search. That's the kind of computation. But of course, this is more applicable combinatorial optimization in general application. But what he ends up using is actually makes heavy use of the for all construct. And it looks to me, by looking at the code, that the reason why he's doing that, and also reading the papers that he's written about this, is that he's using the for all because he can write a user-defined load balancer to balance the load of this very irregular set of tasks over the different nodes in the machine. The code does have, this is an open source code, so you can go check out the code if you'd like. It does use begin and atomic variables to coordinate those asynchronous tasks, but it looks like that's being used in the checkpointing code. So there's some asynchronous checkpointing is occurring in this code. All right. So next example I have here is parflow. So this is a code that I was collaborating with these folks before joining the Chapel team. They're doing a hydrology model. So they're doing groundwater simulation here. The picture that we have up here, this is a watershed in Colorado. And so they're looking at the flow of water on top of the surface all the way down into the bedrock. And how water flows throughout the surface. This is a code that began in 1998. It's more than 1 million lines of C code at this point. So this is C plus MPI code. And for a summer intern project this past summer, Brandon Neff, our summer intern, wrote some of the code in Chapel. So we looked at like where is some of these example problems spending most of their time, and he rewrote in Chapel. And what he was using there is he was using for all for shared memory parallelism. So that's the only task construct we use. But here's another example, just like with CHOP, they were using those user-defined Chapel iterators to do load balancing. Here, Brandon used the user-defined iterators to actually significantly simplify the code that was dealing with boundary conditions. So we have these stencil computations, these large PDE solvers, and we can do lots of interesting stuff in the middle guts. Like us as computer scientists, we love the middle part because we understand that. And then the boundary pieces is where there's a lot of gnarly code out there. And a lot of the domain scientists are having to do various tricks to manage that. And so what Brandon was able to do over the summer is take some of the surface traversal macros that was in this code. There was some really cool stuff in this code. They were using macros in C to separate out like how you do the traversal over the grid from the computation itself. So they were passing in the loop body into these C macros. So it's really clever stuff happening in this code. But it was pretty long and gnarly, as you can see. And he rewrote that to use Chapel iterators and some of the constructs within Chapel, things like domains and tuples, et cetera, to significantly simplify it. And so in the code that he was working with about 800 lines of this 1 million line piece of code. And over on the left is the 800 lines from the C code. And then what he was able to get is a Chapel version that used about 40% less code. And most of that was a reduction in the traversal code. You can see that reduction of that light yellow part of the bar. Now, he did have to add a little bit of code. That's that red slice, which is the interoperability between the C code and the chapel code. But even with that little, a bit of extra code, overall, there was a significant reduction. So this speaks more to the programmability of it. The performance was essentially competitive. So there was some more tuning that needed to be done, but it was looking like it was going to be competitive. Okay, so now let's talk about the coral reef code. And I'm really excited about this one, probably because I've been talking with Scott about it for the past 2 months. He's put it together so quickly. And Scott just started learning how to use Chapel. So he's a climate scientist. He started using Chapel beginning of September is when he started with the team. Okay, and then once he kind of figured out how to use Chapel, was working with some examples, he was like, you know what, I want to do this coral reef image analysis example. And he's using lots of the concepts in the language. So what this is they want to analyze how much diversity is at various parts in coral reefs. Why? Well, we've got to prioritize our efforts to try to save those coral reefs. And so that's what this is trying to do. It's taking satellite imagery and trying to analyze from what we know about on the ground, like how can we save as much diversity in these coral reefs as possible. So Scott has written less than 300 lines of code, and it scales out to hundreds of processors. So he's using, he has access to Cheyenne, which is in Wyoming. It's an in-car machine that's in Wyoming. And he's calculating these maps in seconds rather than days, which is the previous approach. So his collaborators are really excited about this and throwing big problems his way. So what are the patterns that he has in his code? Well, he's got a for all that he's using for the shared memory parallelism within the convolve, and I'm going to show you some pictures. And then he's got a co for all for the distributed memory parallelism. And I actually think he could use a co-begin construct because at the very beginning, he's reading in the image file and he's having to read in this table of how different pieces, the diversity between different pieces. And so I think those can be done, of course, in parallel, and you could use a co-begin. He's not actually doing that just yet. All right, so he's got a mask that he's going to convolve over the satellite image of the reef. It's got an equation to calculate the diversity here. It's essentially an n-squared computation, and he's applying it to every internal endpoint in this image. Right, so there's a lot of work being done here. And the way he did the parallelization is he took swaths of the image and had one task per swath, and those tasks are distributed across the nodes. And then within each swath, he's doing a shared memory parallelism. He's also doing some tricks in that you can do some incremental computation between every time you shift that mask over by a pixel, and so he's able to save a lot there as well. And that's some of the algorithm improvement that he's got. All right, so now let's look at our task graph example. So this is where I was like, okay, well, what is using begins and atomics going to look like? And as Ram mentioned, I've done a lot of research in something called the sparse polyhedral framework. I actually developed the sparse polyhedral framework. And there we look a lot at how do we schedule sparse computations across loops. And when you're doing that, you're going to end up with kind of these irregular blobs of atomic tasks that can be done, and then they have dependencies between them. So you end up with arbitrary task graphs. And so I've looked at various ways of like, well, how do we want to execute these arbitrary task graphs? This is just a toy example, however. This is not one of the bigger examples. So over here, we've got a whole little code that encodes, this is the dependencies of between like 4 little tasks, and then executes them with some asynchronous parallelism and some coordination. So let's talk through how this is working. At the top, you can see that I've got this dense 2D array, A, and in there I'm encoding if a task needs to wait for another task. So A2, 0 equals true means task 2 needs to wait for task 0 to complete. So it's encoding a dependence. Task 2 also has to wait for task 1, and then task 3 needs to wait for task 1. So this little task graph I have, we can kick off task 0 and 1 right away. They can start running, but tasks 2 and 3 are going to need to wait. We then take those dependencies, and I'm just going to encode them with an array of atomic integers. So you can see that in, oh, does this work? Oh, it actually worked. Okay. So I've got this array, num to wait for, of atomic integers. And that's just for each task, we're going to count up how many tasks do you have to wait for. So then we have a sequential loop that is going to asynchronously spawn off all these tasks with the begin. And each task is just going to wait for the number of tasks it needs to happen before it to go to 0. It's going to do its work, which in this case is not very much, just saying, hey, I'm doing work. And then it is going to tell all of the tasks that depend on it, hey, you get to wait for 1 less task now with a fetch add. All right. And so that is the asynchronous example we have. I'm going to just check this time here. Okay, we've been good on time. So any questions on this example? Yeah, hi.
What is the keyword config for in the first line?
What is the key? Oh, config. Oh, this is such a cool feature. So config variables and constants in Chapel, Chapel does the command line parsing for you. So if I declare a variable as a config, like in there, then that means on the command line, I can just say --n equals whatever. Okay, cool. And it'll reset it for me. And so you set the default value for it, but you don't have to do opt-args or any of that stuff. It just does it all for you. It's just kind of a nice general purpose programming feature. Any other questions? Yes.
So all the global variables in Chapel that projected by all the local.
So I think the question is, can all of the global variables in Chapel be accessed by all of the local, like the tasks?
Yes, so all the tasks, everything.
Well, so it depends on the lexical scoping. So if it is a variable that's visible to everything in a module, then any task started in that module can access that variable.
Now that means that like each access will be translated into a message.
Yes, okay, so this is a great question. We're not really talking, I didn't talk much about data today, but your question is like, well, how does that happen? Like if I'm a task and I'm on locale 1 and I'm accessing a variable and the data is stored on locale 0, what happens? Okay, that is when various asynchronous puts and gets are happening to go get that data for you.
Okay.
Yeah, and I'm not gonna stand here because the light is especially bright right there.
That means all the puts and gets will be small messages. I know.
Yes, so there's lots of small messages. And then there are some constructs like aggregation in Chapel that, for example, the Arcuda, that big sort, it's lots of puts and gets, okay? But it then uses the concept of aggregation to make it so that those are aggregated together and you're doing larger puts and gets so that you get the performance. Yeah. Okay, and then question over here.
Yeah, it seems kind of odd to me to see a wait for sitting on something called an atomic int. That looks more like a condition variable to me than an atomic variable. I guess I'm wondering, is that going to just spin and wait for the atomic to reach 0? Is that the concept, or?
Yes, that's what that task is going to do.
So is it like
Yeah.
sleeping?
Well, I
and
mean,
spinning
so with the atomic variables and the sync variables, I think, this is it's an educated guess on my part. I can double check with the team, but those variables do have, they will yield, they will have the task. So when you call wait for, the task is going to yield control so that something else can get time sliced in. And so the runtime is going to help us do that. And then magical runtime stuff happens under the covers. It's not magic, but it's just stuff that I don't know off the top of my head. There's also sync variables. So using atomic ends is what I thought of on Monday.
Right, it just looks weird for me to see a wake for sitting on an atomic.
Well, I'm glad I could come up with like something novel
Well,
to show you
sync
today.
if you did a sync variable or something called a sync variable, I would have said, okay, that seems a little stranger.
Yeah. I'd have to think about how this would work for sync variables. Any other questions? Yeah, because with the sync variables in Chapel, you do have like, is it full or empty type thing. I think I may have gone with the atomic ends because I wanted to be able to do this like atomic adding and subtracting to it. And I'm not sure I could figure that out with syncs quicker than that. All right. So I think there is some interest by most people in our community these days for how do we handle GPUs. So this is my one slide on GPUs. There's a lot of information on this slide. I don't know, Patrick, do we make the slides available afterwards? Is that how?
You can if you want.
Yeah, so I think probably I've got a lot of links in this talk that people might want to try out. And so we've got two kinds of support for GPUs in Chapel. We've got some beginning support where the Chapel compiler takes for each and for all loops and compiles them down to CUDA kernels, essentially. Not CUDA kernels, compiles them down to LLVM. Right now we're mostly running on NVIDIA, although we're exploring and have an initial prototype for AMD. We're also looking into Intel. There's also the capability of Chapel code calling out to CUDA, and actually Vivek Sarkar's group has done a lot of that. He's got like a GPU iterator in Chapel and done some other work. Josh Milthorpe and some others at Oak Ridge National Labs are looking at getting our CUDA to run on Frontier, which is 97% of the compute power in that machine is GPUs, AMD GPUs. And they're using a lot of Vivek Sarkar's group's work to do some of that. And I've got a couple links in here with examples of how you can have Chapel code call out to CUDA through the C interoperability. Some of the key concepts here that show up on the right-hand side, which is some example Chapel code that works right now, is we want to use this locale concept. I can't remember who asked about that. I think you asked about this. Like, how do we map tasks to GPUs? Okay. Well, we're going to use this locale concept. And so you have a locale to kind of represent a node or a socket, and then you're going to have some sublocales to indicate what GPUs you have associated with it. So if you look in this code, we've got if here, so here is referring to the locale we're on, the current locale we're on. If here.gpus, that's a sublocale array. If its size is greater than 0, so does that mean if we have one or more GPUs, then let's go ahead and set this operate on variable to an array of those GPUs. Okay. Otherwise, we're just going to put the current locale, the current CPU in that array. And so with this statement right here, you've essentially set up an array of locales, either of GPUs or just of the current CPU that you're on. And then your code that is assigning tasks to those locales does not have to change. All right, it's just going to do its thing. It's going to say, okay, I'm going to iterate over that array of locales. And on each of those locales, I am going to do this computation. And so we've got just a small array being declared. That will be actually, if you are running on GPUs, that will be allocated on the GPU. And then this for each will be turned into a GPU kernel. Okay. It'll be kicked off. And then this write len will happen back on the CPU. All right. And we've got various diagnostic calls, so you can see like what actually executed on the GPU, et cetera. So for more information about the GPU support, there's this tech notes link about GPUs, and that's got the most up-to-date examples there from that subteam. All right, so with that, I'm going to wrap up with some takeaways. So Chapel is a general purpose programming language, and it was designed from the very beginning to leverage parallelism at all different levels and of all different kinds, including asynchronous parallelism. It's being used in some large production codes, and it's got both the performance for those codes and the programmability from what we're hearing from the developers and from what we're seeing from people like our visiting scholar who picked up Chapel very quickly and is now being quite productive in his science, is climate science with it. We saw some of the task parallel patterns in various applications here. Whoops. This is the magic table from the talk. And with that, I'm going to wrap up and take questions. And I just want to point out there's a couple more slides that I'll add to the PDF for this with just some more resources, including, I did a tutorial a couple weeks back at the University of Arizona for their HPC Center. And there's lots of different Chapel code examples we went through, and we have a container that people can run so that you don't have to install Chapel on your laptop. You can just use Docker or Podman for that. And there's a bunch of links. So, questions?
Thanks, Michelle.
All right.
Questions? Yes, one question. So I wonder how does the distributed memory model looking?
So the distributed memory model?
Yeah.
So are you asking like how is the data distributed?
Yes, it's like
Okay.
using any PGAS.
Yeah, so it's using PGAS. So one of the things we use in the backend is GasNet. We also use like libOP for doing the puts and gets underneath it. Well, but you're asking specifically about like, how do we know where the data is? We talked about tasks today, but I didn't talk about data. So let's imagine that those 4 locales, if you started your computation up with 4 locales, your main is going to start in that locale 0. And anything you declare in that main is going to be allocated on locale 0, unless you are declaring something like in a distributed array. So in Chapel, there's this concept of the Chapel iterator, which helps us map tasks to different locales, okay, and to schedule tasks in an orthogonal way. There's also a concept on the data side of things of domain distributions, okay? And so you can declare, there's some built-in ones, not built-in, they're in a library, but there's some ones in the standard libraries to do block distribution or cyclic distribution of an array, et cetera. And these can be any multidimensional array that we can distribute. So if you declare an array as being distributed, then even though that's being declared in a task that's only on one locale, the array is actually going to be distributed across all the locales. And the programmer can control how that distribution is within the array.
Yeah, thank you for the great talk.
Oh, thank you.
I think we've all been watching Chapel for more than 10 years.
Okay.
I was doing that when I was doing X10 and OpenMP. It's never made clear to me, where Chapel was aiming its language. Is it high performance computing? And if so, why are you not, or maybe you are already porting a lot of high performance programming workloads? I mean, I know you are already from your talk is. But what about, you know, the workloads that the DOEs use, like Lomax or things like that? Are those also like the popular ones that they always use to judge as a benchmark for
Like for
purchases?
procurements?
Yeah, for procurement.
Well, so
Are you
Arcuda is being used for the Arcuda, which is that data analytics package that's in production, that is used to judge procurements. You know, there's a lot of momentum with some of these codes. I mean, like with the Parflow code I mentioned, it's been around since 1998. It's like it's older than both my children who are now adults. Like, so you know, I think asking somebody like take your million lines of C code and go rewrite it in a different language is not right. It's not something that's going to happen overnight, if at all. So, but I've been working with a lot of scientists throughout my career who, you know, I've been working with some scientists who have these established very large codes. And I think some of the advantages is as we have to rewrite parts of those codes to leverage GPUs, I think we should be looking at the various kinds of the variety of tools that are available and what's going to help us out there. And I think that Chapel has the potential to help deal with the GPU situation that we've got going on. All right.
So you are targeting high performance computing.
We're targeting high performance computing, but we're also targeting people developing on their laptops. And so really so my personal kind of where I'm coming from is working with like astronomers and bioinformaticists and life scientists of all kinds, where they are writing lots of Python scripts, Perl scripts, MATLAB scripts to do their analysis. And then all of a sudden they realize, oh my gosh, I have so much data that I want to do this analysis on. And those tools that I just rattled off can't cut it for me. Okay, but the codes that they're writing are, you know, they're just getting started in thinking like, hey, I need to take advantage of HPC. And so I think there is folks like Scott Bachman, who is doing climate science. So of course he's got the simulation codes as well, but even climate scientists, even the people with a bit large simulations, they're having to analyze the data resulting from that. And so those codes tend to be not 3 decades old, they tend to be like 3 weeks old and are much smaller. People are building them up, but they're coming very quickly to the realization that they have to process massive amounts of data. And so a productive high-level parallel programming language that you can start out on your laptop, so you can do the data analysis initially on your laptop, but then when you say, okay, now I need to process all this massive amounts of data with a Chapel program, it's just going to now work on a supercomputer. Yeah. Yes.
I mean, it's important to note that actually Chapel is one of the 3 programming language projects that it's the only one that has survived.
Yes.
There used to
X10,
be 3
Fortress.
funded by either DoD or DARPA, and 2 of them basically never delivered. There's one that was called
X10.
X10.
And Fortress. Yep.
Yes, and Chapel is the only one that survived. And it traces its roots to ZPL, which was Brad's PhD thesis at the University of Michigan.
Yes.
But the other thing to keep in mind is that high-performance computing is now essentially ubiquitous. It's everywhere.
Yes. High performance computing is ubiquitous.
So everybody needs to figure out what to do.
On the coral, I think it was, you mentioned
The coral reef.
yeah, and you mentioned the time to solution or whatever was much faster. So
Yeah,
was that
seconds
because
instead of
they did
days.
it on HPC or just from improvements from using?
So the improvements came from 3 different things. So, and I haven't, Scott's not a computer scientist, so I was like, well, how much of this is from the algorithm? How much of this is from Chapel? And how much of this is from running on Cheyenne? And he's like, I don't know. It used to take days,
Okay.
and now it takes seconds.
Okay,
Right, and so.
so the advantage was just going to the.
Yeah, so I think that there was a lot of components at play there. I think the algorithmic piece was pretty significant. that was probably a couple orders of magnitude there just by itself, the algorithm. He's got this interesting like incremental algorithm that he's doing, so he doesn't have to do the whole convolve each time. And so that's cool. Turns out he did find that that was an approach that had been previously published, but for some reason wasn't being used in the commonly used MATLAB implementation. And then I actually don't know the answer to your implied question of, is that MATLAB version, was that being run on a high performance computing, like on a supercomputer like Cheyenne? I don't know the answer to that, so I'll ask Scott that. And then, you know, Chapel is compiled. I know MATLAB, there is a just-in-time compiler that MATLAB has, which can help, but you know, Chapel, there's been a very strong push in the past 10 or so years to get Chapel to be compliant, and it's doing very well there. Yeah.
So I guess HPE Cray has been responsible for 2 parallel programming languages that have survived in the future, the other being Fortran.
Yeah, Fortran with Cray, right?
And I guess Achilles heel for Fortran has been a spotty landscape in terms of compiler support. HPE Cray has been in the leadership in that regard. They developed it and they've always kept up with the standards, but not all the other vendors have. With Chapel, what are the pros and cons of, do you think there should be other compilers, or are there other compilers for Chapel? And
you asked me such painful questions. Okay, so
maybe they don't need to be.
No, I mean, should there be other compilers for Chapel? I would really like there to be other compilers for Chapel, but there aren't. Yeah, there is just the one compiler right now. We don't have a standards process ongoing yet. We do have, as one of our near term, and by near term I mean within the next year or two, we're planning on starting a Chapel language board, so to bring in some external people to start a process of getting input on the language as it evolves, and so that we can start moving toward eventually, you know, longer term, moving toward some kind of standardization process, because that is something that would give a lot more confidence, especially to some of the communities we talked about, like DOE communities, for standing up their really large codes and starting to move some of those really large codes over to something like this.
If I can follow up, the flip side is there's no Python standard, right? But it's wildly popular.
Thank you for mentioning that too. I'd also like to point out that Python started in 1994, so Chapel is still 10 years younger than Python. We've got plenty of time to explode,
whereas
just like Python.
Is now Medicare age.
That's right. All right, I think you had a question, and then I saw your hand too.
Yeah. Is there any API in Chapel that allows programmer to define the task?
Is there an API to do what?
Define tasks and dependency between tasks in Chapel, because I think most of the code that you presented here is everything about using Go for all. It's basically or join approach, right?
Right.
It's not really.
Yeah. So that's why I wrote this little example.
Yeah.
Because if you're just going to do an asynchronous task, you're going to use this beginning construct.
Okay.
And then you're going to use sync variables or atomic variables to coordinate between those asynchronous tasks.
I see that apart from these mechanisms, there's nothing else, right? And is it the only way to maybe synchronize?
I mean, what kind of thing are you thinking of?
I'm thinking more about maybe something like an MP task, where you can define different tasks and dependency between tasks, this kind of thing. Like things like maybe you can define something like a DAG.
Like you can define it. So this little example code defines a DAG.
I see.
This shows how you would, how one might. This is one way you could define a DAG in Chapel.
And is it possible maybe to say that, okay, I want to have this task running on this CPU, or is this something that's kind of...
Yeah, so then that's the next slide where it would show like how you could do. So you can, so your question is, can we do begins on GPUs yet? Not yet. Not yet.
Okay. Okay,
Yeah, we don't have the ability to do begins on
Yeah.
GPUs. So the
Yeah.
GPU support is fairly young, it's like within the last year and a half, and we've only had like one person on, 1.5 people on it. So that's gonna take a little bit longer.
One last question.
One last question.
Yeah, it's sort of related to this, how flexible is this locale mechanism? So I think I've seen locales being CPU cores or GPUs. Would it work to, for example, run Chapel on multiple VMs in the cloud?
On multiple VMs in the cloud. I doubt, I have not seen that use case. The way locales have currently been used in Chapel has mostly been a very flat model. We are going to move, the idea of having hierarchical locales has been around for Chapel for quite some time. And I think we're going to see its first instance with GPUs, but I'm guessing it's going to be mostly 2-level. Now, running on VMs in the cloud, we do have like a runtime backend that runs on Amazon, EFA uses that. And so there, the idea is you can launch your different locales on different, I'm not sure if it's different VMs in the cloud or whatever is represented, whatever the node representation is in the cloud. And then you can do pits and gets there, but we haven't spent any time optimizing that.
Okay, but so it would be possible to.
So it's possible, right, it's possible, and I think we actually have the functionality in our runtime currently to do it, but it's only been done kind of at the prototype level.
Thank you.
Yeah, all right.
Thanks, Michelle.
Yes, thank you everyone for your time.
We have a short break. We'll start at 10:30.